I'm Tim Ventura, and we're joined today by Dr. Thomas Cooley, Chief Scientist at the Air Force Research Lab's Space Vehicles Directorate. Tom has a PhD in optical sciences, an MS in applied physics, and an NS in electrical engineering, and a 25-year career with AFRL. His roles have included program management, the Space ISR Mission Lead, Senior Scientist for Situational Awareness, and for the last 5 years, Chief Scientist in the Space Vehicles Directorate, where he assists with the planning and execution of an annual $165 million Air Force Science and Tech program budget, and serves as the OSD Space Community of Interest Lead for all space-related science and tech issues across the DoD. He joins us today to discuss advances in hyperspectral imaging and how those are empowering ISR advances within the DoD and offering new capabilities to science and industry as well. So Tom, welcome, sir. Let me start out by thanking you for your career of service. I always like to do that. And let's start with a definition of hyperspectral imaging. In terms of sensing and imaging technologies, so we've got traditional photography along with LiDAR, radar, infrared, ultraviolet, terahertz, and even longer band technologies. So in today's world, what does hyperspectral include? And how do you expect that imaging spectrum to grow as this technology advances?
Great. Well, thanks for having me, Tim. I'm really happy to talk about hyperspectral imaging. I actually prefer the term imaging spectroscopy. I think the way to think about imaging spectroscopy is that we're really doing a remote sensing observations of a surface, materials, or anything that is emitting or reflecting electromagnetic energy over a broader spectrum. So we're really doing that laboratory spectroscopy for those who have had an opportunity to do that type of thing. So doing material identification, chemistry, really, the chemistry identification, identifying chemicals, because we are able to understand what the various absorption and reflection characteristics of that material are, and so we're basically bringing that to space, or an airborne system, so that you can do, if you will, surface chemistry from space. Right. That's maybe one way to think about it. You can also you obviously see a lot of the atmosphere, depending on what wavelengths you're looking at, but it's that's one way to really think about it. And so if to try and take up on your question in terms of LiDAR or radar or many other types of technologies, those two are active remote sensing. So in other words, you're sending out a signal that you know what it is, and then you're looking for the return of that. So whatever that reflection is. And of course, there's a time domain aspect of that that's very useful with both of those technologies. But if you're looking at a passive remote sensing, sorry, my Apple Watch thought I'm talking to it. If you're talking about passive remote sensing, then you're really thinking about anything where there's either thermal infrared or solar reflected energy, and so you don't have that extra dimension or the responsibility to send out a signal that again that drives power, that drives range, that drives a lot of things. So an imaging spectrometer is really taking whatever wave bands you can sense with your detector and looking for those emitted, those upwelling to your sensor, the spectra, and then trying to diagnose and really descramble what's going on based on the total spectrum that you have. So I don't know if that's enough of a sort of trying to look at the way in which I think about, and many people think about, the passive remote sensing communities that have emerged over time.
Oh yeah, absolutely. Well, and again, I mean, this is a really big topic, right? And so that makes it kind of difficult, I think, for kind of a short interview. So I definitely appreciate your help. Again, what I'm trying to do is just lay out some of the fundamentals for the audience and then try and see kind of where it goes from there, you know. But so in terms of the Air Force, some of the components of this have been around for a while, right? Like infrared imaging is in use in many aircraft. Radar imaging has been around since World War II.
Right.
So I guess is one of the biggest challenges in terms of this hyperspectral, or the imaging spectroscopy, as you described it, is one of the biggest challenges the integration of these into kind of a single image? Is that kind of the challenge?
Yeah, well, I think the you know, if we think about the history of remote sensing, and so I'm going to try and capture it in that term. You know, we start with black and white imagery, right? Just your very basic camera. Then you have the advent of color. You're adding color to that, and of course, hyperspectral brings us to, you know, many colors that go outside of what your eye is sensitive to. Infrared, again, when you think about an infrared image, we're really looking at a heat map, typically, of, you know, oh, you can see a warm body against a cold background, that kind of a thing. And that's typically just, again, a single band. In other words, it's just a black and white image as it's portrayed in some sort of a media. What we're really talking about in terms of a hyperspectral image is more bands than you can display. So now the brain is not, the eye and the brain are not able to discern more than, you know, 3 primary colors, right? That's what this video screen is that I'm looking at now. It's 3 primary colors. And we, the eye and the brain have evolved to be very good at processing that. What we are able to do in a hyperspectral imager is there is some redundant information. In other words, we're collecting you know, many bands between the range of the human eye. So we might have, you know, 10 or 15 color bands within that. So you're going to get, you know, various shades of green and blue and so forth, and we'll measure what the response is, what the incoming response is to the sensor. But what's more exciting is when you get outside of that, and if you think of the electromagnetic spectrum and some of the sensors that we talk about building, taking advantage of going into the ultraviolet, through the visible spectrum where the eye is sensitive, and into the infrared. And so you have near infrared, which a lot of times you might see, for example, vegetation is a very bright signature of reflectance in the near infrared. But as you go farther out, then you get more interesting and more subtle signatures of minerals, and the atmosphere becomes opaque. You have water vapor absorption in the atmosphere. And so you're able to discern, in fact, how much water vapor there is between the sensor and the scene. You're able to, I'll say, descramble that, because you can see how big a dip there is in some of those water vapor signatures. So we know how much water vapor, or how much it attenuates signals in those spectral bands. And so you're able to basically reconstruct and make sense of that, because now you have not just, you know, red, green, blue kinds of imagery, but now we can see it's as if your eye was sensitive to, oh, in this color band it's really black, therefore there's a lot of water vapor, and I know that. And then it's, if it's not, then oh, it's a dry scene. So that's the kind of thing that we're able to discern with an imaging spectrometer.
Oh, well, so let me give this a try. Actually, I'm going to jump around just a teensy bit in my
Of
questions, but
course.
I want to try and share my screen if I can, and hopefully you can see this for me.
Yep.
So I wanted to put this up, and let me see if there we go. Yeah, the images produced by hyperspectral imaging, or again, imaging spectroscopy, they're a little bit different than a traditional photograph, at least most of the time. I understand that these are represented primarily as these three-dimensional data cubes, and they're comprised of stacked images of the same scene from adjacent wavelengths. So the dimensions of this data cube are kind of built up from the satellite crosstrack and the wavelength range, right?
That's right.
Yeah, so this is one I found a couple of public domain images that I thought I would put out there for the audience. This is kind of another, these are both from the ESA. And again, these are what's called data cubes. And I guess as people go farther down them, as you go farther down that data grid, those colors would change. And it's because it's representing things that aren't visible to the human eye. And in this one, I guess you can see the intensity, and it's showing the wavelength as well. And then in this final one, I think it's pretty much the same thing. It's trying to show the near IR and the UV bands on the left there in contrast to the standard RGB that we're familiar with, like on computer screens.
That's correct. Yep.
Yeah.
Yes.
So let me go back to this one. Do you think you could tell me a little bit about the data cubes? Because I think that's primarily what you guys work with at AFRL, right?
Yeah, and it's really we're standing on the shoulders of many giants in the fields that came before before much of the AFRL contributions, but it becomes a blending of different technologies and backgrounds. So I believe this is probably from the NASA Hyperion satellite, or it could be also the NASA Avaris airborne sensor, which was really the forerunner of most of the field. So my admiration for that team. Rob Green and others that they're at JPL have done an outstanding job of continuously improving that sensor so that we can get to where we're really doing again chemistry from a high altitude airborne system. So what we see here, of course, is the image of the, I think it's a volcano scene. You see something that the eye is used to seeing, an image of that area, and you can visually spatial out roads and other things going on there. What the imaging spectrometer is really all about is the dimension that's going back into the screen. And so what you see here is a rendering that is first starts with the ultraviolet and the visible wave bands. So that's the types of greens and other things that are rendered in that front picture. But as you go back into that, and you can see that the intensity grows. I'm not going to venture how far back, but 15% back into the data cube. Now you get these high responses, and the reason what you're really seeing there is that infrared vegetation, high reflectance coming online. So again, we see the color green, and that green is usually it's really subtle feature in terms of vegetation having a reflectance in green in terms of the spectra. If you then look past where the visible eye can see and go into the infrared, then you see this huge spike up of reflectance. So we talk about the albedo. So albedo just means, it's a fancy term for reflectance. But as you go into that infrared, then you have this very high reflectance from vegetation. And so as you go back into that cube, you can see that that's what's going on. That most of that area around the edges of the data cube are vegetation. And so you see that. Then you see a very dark spot. You see a couple of dark spots. Those are going to be atmospheric features. Those have nothing to do with what's in the scene. It's because now you've hit some water vapor or other absorption that are in the scene. So in other words, when we actually just take the radiance of all of those spectra, the way this is collected, then you're just getting, I'll say a very dull, uninteresting scene in that water vapor. Now, what's uninteresting in terms of the visual eye actually has some subtle features that we can, as I was describing earlier, we can start to pull out. Okay, how much of that, what is that radiance level? And we can start to determine and actually map out what's the water vapor in that area. So for example, if that volcano is at a high altitude, we're going to see, and of course we can't sort of dive into this, but the data cube analyst would be able to drag their cursor over and look at the spectra right there at the top of the volcano's edge, and they might be able to see, aha, in fact, that has much less water vapor. Why? Because it's a much higher elevation, and water vapor is a fairly heavy molecule, and so there's not a lot of water vapor at, say, 10,000 feet to the top, where the airplane is. But those areas around it are maybe at 1,000 feet elevation with the vegetation. And so there's a much denser cloud of water vapor, if you will, in the atmosphere. So you can start to, discern those types of things from those, if you will, dark regions. As you go farther back into that, then it becomes much more driven by the particular chemistry of the vegetation or the soil. You might be able to pick up on nitrogen depletion in the vegetation as you get farther back into some of the spectral signatures, which now you're getting outside of my area and into biology of where you can find those particular spectral signatures. And that's going to be based on a lot of measurements of I'm going to say biologists going out into the field, taking spectral measurements of and then doing the chemistry of, is it depleted from nitrogen, or are there other things going on, by analyzing that in the laboratory and then correlating it with the measurements that they take in the field. Once you establish an understanding of what that is, then you can go to, again, something like this, and you can say, okay, well, we see areas that are depleted of or richer in terms of some of the minerals that are manifested in the vegetation. So it's there's a lot going on here that. And then as you get out into the shortwave, again, there's going to be signatures from minerals. So you're going to be able to discern, if it wasn't all vegetation, you'd be able to discern things, calcite from aeolinite and all these other, and again, now I'm out of my field into geology, but I know just enough to recognize that those are the types of spectral features that we're going to be able to start pulling out, those different types of chemistry bonds that are present in those minerals, and those then manifest themselves in the reflectance spectrum from a sensor like this.
Yeah, well, and this is one of the reasons that this is so exciting. Let me stop the screen share here, and there we go. Okay, we're back. But yeah, for me, this is one of the reasons so exciting, because I have a computer background, right? And so I do photography, and I always look at photography with an eye towards, okay, this is data. We're capturing data, right? Standard RGB. And when you start to look at imaging spectroscopy, it's like, okay, well, you're capturing so much more data, and then one of the questions for me, I'd kind of mulled this over. The data cube is an interesting way to represent it. I've seen other ways to represent this as well. Sometimes they just kind of almost like pick a deck in the stack, right, for frequencies that have meaning, and they'll just use that as a standard RGB image.
Right.
Is there kind of an industry standardization, I guess, emerging for how these are rendered, how these non-visible bands are typically rendered?
Yeah, well, I think the best way to answer that question is to talk about Landsat. So Landsat started back in the late 60s, early 70s when they started to build it. And so Landsat 1 was the first multispectral sensor. And as we went through and advanced in technology, we added different spectral bands to Landsat. But in fact, in I believe it was 1992, Congress passed a law for the Landsat data continuity mission. So that we would continue to have this global record at a 30-meter ground sample distance. So that's the size of the pixels as projected on the Earth. And with similar spectral bands. So now we can really do analysis of deforestation in Brazil, right? Or anywhere, or urban growth, or all of these types of things, because we have this synoptic. I'm going to say it's synoptic because it's all essentially looking at the same, but there are some subtle differences. Again, we've enhanced the spectral, the number of multi-channels. And to your question, and out of that Landsat, out of those Landsat missions, grew a community that dealt in Landsat. They very much understood it, and they did choose a particular types of rendering of those. And I'm going to say 7 bands because that's when I was in graduate school. That was essentially where Landsat was at that time. And so the red was always the color red on the screen was always used to display the infrared. So if you looked at the scene like we just were looking at with a lot of vegetation, it would look very red because, again, that infrared albedo is very high. And so the other colors are relatively a low albedo, and so it always so vegetation looks red. And so people who became accustomed to looking at Landsat images would understand that. They would look at a field and or agriculture, and if it was all red, then it's probably very healthy. If it's not, then it's not very healthy, right? That kind of, again, really simplifying for the brain the ability to process that images, that image, a picture. Again, brain's very good at that, and so we use that, and we start to make that correlation. And so what has not really happened, at least in my understanding of hyperspectral, is that you really have so many spectral bands. You're not just taking one spectral band and displaying it. What we're really doing now is doing, to your point, is doing some advanced processing on each of those spectra. And so what we know, what, let's say, again, let's take a mineral, kaolinite. Again, I'm not an expert on these, but let's just say you're looking for kaolinite in Death Valley. So there's not a lot of vegetation. And so what we would do is we would take the spectra of kaolinite from laboratory measurements, and we would run a matched filter. So essentially we would run it against all of those pixels and see how well does it match. You could do spectral angle. There's a number of ways of processing it. I won't even get into it, but it's basically it's very straightforward linear algebra to look how close is any of these pixels to our exemplar of kaolinite. And therefore we would produce then a map. And so it would be very, say, bright for areas that look very much like kaolinite, and very dark if it doesn't. So in that case, then your vegetation would not look at all like kaolinite, and so it would be very dark. And anyway, you do a mapping, and I'll call it a heat map of kaolinite. So those are the types of things that you're able to do instead of just, again, a single color. Now we're saying, no, I'm looking for a particular thing, a particular type of material, and I'm going to go search the data cube for that type of material.
Yeah, yeah. Well, thank you so much for the in-depth description of this. Now one of the things you just shared with me is you quite literally wrote the book on this. So this is probably a good time to bring that in.
Oh, yeah,
Do you think you could
well,
show us your book?
Yeah, I did. So with some colleagues of mine, and with the University of Cambridge Press, we put together a book that covers all of the, from processing, the basic physics, sensors, all of that type of thing on hyperspectral imaging. So yeah, we're pretty proud of it. It's not a quick read, but there's a lot of examples and that kind of thing of how hyperspectral imaging can be used, and again, what some of the processing that you would want to employ, including again, using atmospheric models to be able to pull out the atmosphere, because the atmosphere can confuse your spectra, right? So you want to be able to identify what is going on in the atmosphere, pull that out so that you get to, if you will, at surface radiance. You pull those many layers of what's going on in the atmosphere to get to the surface chemistry that you're interested in.
Yeah. Well, and what I will do is I will research links and try and find as much as I can and put some links so that people can purchase a copy of that book. And I'll put them in the interview links as well. Okay. And I'm going to jump forward in the questions a little bit because we're pushing on time. But, I wanted to ask about, I wanted to start to touch on some of the commercial applications of this.
Absolutely.
And the reason is the cost and the size of this technology seems to improving, and that shouldn't be a surprise, right? I mean, advances in tech are bringing costs and size down on all sorts of information processing technologies. Right. So one example that I saw was a company called BaseBec sells HSI imaging systems now. They actually fit on drones for about $5,000. And in that particular example, I don't think that they have the complete spectra, right? There are always trade-offs and limits. But
that's right.
But I'm wondering, is that an indicator that we'll see more of this hit the commercial market, or will it remain limited to niche applications, do you think, like IR photography?
Yeah, I think so. Your cameras that you're taking your standard pictures with, most people have a smartphone these days with built-in cameras, and they've gotten quite nice. Those are based on a silicon focal plane. So the detectors are all silicon, and they're very responsive, and they work very well for red, green, and blue. What becomes so that the sensor you just talked about is a silicon-based detector. Now, the silicon will go out into the near infrared, what we call the near infrared, about to 1 micron wavelength is where its response drops off. So it'll be responsive from the blue or even going into the infrared out to about 1 micron. And so that's very inexpensive to build that kind of a sensor. And so we do see a lot of commercial applications coming forward. And you're able to look at, again, health of vegetation. A lot of things can be gleaned from that type of imaging spectrometer, just with that, I'll say, relatively small spectral band. That is, again, roughly 400 nanometers to 1,000 nanometers. The more exotic, to really get to what you're talking about, is and you get to much more expensive cameras when you go farther out into the infrared. The ultraviolet is actually limited mostly because of the atmosphere, because you get into Rayleigh scattering and all. Your atmosphere becomes essentially opaque as you get farther into the ultraviolet. But as you go into the infrared, that's not so much the case. You can continue to go, and so it's how far can you build how well can you build a sensor that has response out into the infrared. And you get into the thermal infrared, and you can even keep going into the terahertz region. That gets really exotic, because then you have to cool your detectors down to very, very low temperatures, right? That's that, and again, that gets into really the James Webb type of cool it down to 4 Kelvin, which just getting anything down to 4 Kelvin, it takes a lot. So you're probably not going to find that in your Best Buy. But you can get infrared detectors. You can get infrared goggles, right? And those go out. Those are typically probably INSB, and that's the material, and go out to about 1.7 micron, and they have some response. And you can keep going out into the midwave and long wave infrared. But the building a sensor that can take that entire spectral, from ultraviolet to long wave infrared, or dare I say, go out to the very long, what we call the very long wave infrared, 20 micron wavelengths. Building a sensor that can manage all of those is very, very difficult. You really get into building it based on your focal plane response, based on the cooling requirements. So you're probably not going to see something that does the entire electromagnetic spectrum, but it would be a composite of, maybe a silicon, because silicon's cheap and easy and does a beautiful job in certain wave bands, and then other types of detectors going into the infrared and so on. So so that's in terms of commercial applications. So I think what we're going to see first is the commercial applications based on those easier to reach spectral bands, and I believe that's exactly what we're seeing. Again, vegetation. So if you were a farmer looking to see again what the your crop yield or other things, the stress from insects, that type of thing is very easy to spot, if you will, with some of those again, inexpensive cameras. As you get into like mining applications, again, if you want to look at some of those shortwave signatures for discerning kaolinite from other things, and it's not like kaolinite's it's not gold, then you're probably going to need to get out into the shortwave infrared, and so that's going to be a more expensive camera.
Yeah, that makes complete sense. There are definitely mechanical and technological limitations on what these sensors will do, and then in terms of, like you'd mentioned, the silicon, right? Like I understand that quartz will pass UV, but your standard glass lenses, that they may pass a little bit, just enough to cause problems, but they don't pass much, and then IR is kind of the same way. And then there are also focal issues, as I understand things, and that would probably be a reason to have multiple camera housings, right? Because you have different focal lengths that play a role.
Yeah, well, what you can, for a given wavelength, you can build your to get a focus of whatever wavelength that is, based on the index of refraction of the lens, right? That's what it is. The problem is that when you're spanning this huge electromagnetic spectrum, there is no material that has a constant index of refraction across that entire spectral band, right? So it might have an index of refraction of 1.5 in the green, and but as you go out to the farther into the infrared, that changes, right? It's 1.3, and so that means the lens that you make will have a different focal spot, a focal length for that same lens. So you can't image and put it on the same focal plane. You have to accommodate for those changes. So it does become much more complicated, and that's the field of the optical engineers who are trying to figure out how do you balance those things and get a high quality images across a wider spectral range.
Yeah, absolutely. One of the reasons that I'd asked about that was, and I know this is kind of pushing outside of our area of expertise for this one, but one of the things that I've noticed is your iPhone camera, right? For instance, they keep improving, and they're putting this market pressure on the Nikons and the Sonys of the world who make DSLRs. And so I thought, well, is it possible that they may start to push more into some of these more exotic technologies to try and, keep their market share, I guess, as high-end imaging, and
that's a market question for them, but I think it's an interesting one insofar as, is there do human beings want to see images in the infrared? Because it's going to be a little confusing to the brain until you get used to seeing that, right? I mean, and again, we talked about the Landsat community that really began to understand that, and they could process that very readily. But most folks don't want to do that. They just want to see something that is a natural rendering as their eye would see it. So that's the challenge for those marketing engineers. If they want to move into that. But I think for the community that wants to go directly to applications, we're looking again more at looking at the spectra, and how can you pull out the information? Where is the information spectrally, and then how do you best pull that out?
Oh, okay. And for the mass market, I guess there are also some ethical concerns, right? And one of those was Sony had a hybrid IR camera in the early 2000s that could, in some circumstances, could actually see through clothing. And if I remember right, they ended up pulling that from the market and replacing it with a camera that wouldn't do that. They change things just a little bit to get around that. But
Yeah, well, I mean, the whole terahertz is what they use in the security at airports. That's because it will penetrate through clothing, and it doesn't give you a sharp image by any means, because again, it's a very long wavelength. But it's certainly there could be some of those concerns. I think for what we're looking at in terms of just, again, surface chemistry, we're still in, I would characterize it as a research stage. What is in the realm of the possible? What are all the applications you could use them for? And as with every technology, you can use it for good or ill. And
yeah.
so we want to obviously use it where it's appropriate for good, and not for nefarious reasons.
Oh, absolutely. Well, and what you described with Landsat, that sounds like a perfect example, right? Where you're able
Yeah.
to take this long-term imagery and look at change, change in surface chemistry, change in, environmental quality, things like that. You're
Right.
able to look at that over a period of decades in time. So that's
That's
that,
right.
yeah, that's definitely
Yeah,
for
and
good.
that kind of an archive becomes very important for us to be able to, again, and as we think about the future going into a more of an imaging spectroscopy rich world, what are the kinds of things that we're going to be able to pull out, right? Of in terms of you mentioned water quality, hard to see from just a multispectral image, but we can start to pull out, again, very subtle features of small amounts of chemicals that may be included, and that might change over time. So those are the kinds of things that again are very exciting to me, and I think to the research community, so that we get a much more validated and assured way of making these types of measurements.
Wonderful. Well, Tom, thank you so much again for your time. Let me close by asking, what comes next for you personally? Are you continuing to do work in this area? Or have you looked at writing another book on this?
Oh,
Are you,
I don't know that I want to write another book. It's a lot of work. Um, I think for me personally, I'm having moved into the role of chief scientist. I'm really looking at space holistically, and the tremendous amount of energy and excitement and opportunities there are in space. The billionaires here in the United States have certainly helped to advance that and put some excitement into that. But it's so true that we're only just at the beginning of being able to really take advantage of the access to space. That's been a major hurdle for us. The cost of getting a kilogram or a pound of anything into space has plummeted, thanks to, in large part, to SpaceX and some of the other advances that we've seen. So that's opened up a world of possibilities. You can now start doing things from space that were not considered even possible, or certainly not economically feasible. So as that changes, we're seeing just a lot of different entrepreneurs and folks thinking about how they can use space either as a platform to observe Earth, or in fact, mining asteroids and other things that are just we're just at the beginning of some of that, building things in space. We're looking at how can you harvest the sun's energy, because once you get above the Earth's atmosphere and into space, then you've got it 100% of the time, and there are no clouds, right? How would we be able to utilize that for either to beam the power here to Earth? And this is an idea that's been around for a long time. So to answer your question, there's a tremendous amount of opportunities that are emerging, and so I see myself, again, watching that, understanding how that's going to shape opportunities, not just for the Space Force that I currently work for, but for the broader opportunities for the country and for mankind.
wonderful. Tom, thank you again so much for your time today.
Absolutely, a real pleasure, Tim.